Hey guys, this video we're just gonna go through the solutions to assignment 1. Okay, let's see. So if the function was not well defined, you only needed to tell me one reason for that. Okay, so in this, you can see like this function is not well defined for a couple reasons. Okay. Right. So let's see. It's not well defined. One reason is, so I can say f is not well defined. Actually, I guess for like 3 different reasons. First reason might be f of 2 over 1. We use a representative 2 over 1. The function says that it should be 3 times 1 over 2 squared. 3/4. But f of 4 over 2, that's just 3 times 2 over 4 squared. 6/16, not the same as 3/4. Okay. So, but 4 halves and 2 is the same number, same rational number, but we have 2 different values for that, so it's not well defined. Okay. So that's one reason. Okay, you could have also said that f of 2 over 1, which is 3/4, is not an integer. So it doesn't lie in the codomain, so it's not well defined for that reason. And you could have also said that f of 0 over 1, which is supposed to be 3 times 1 over 0, is not well defined because 3 over 0 is not defined. Okay, either of these were fine. Okay. For part B, you could have used either of the second and third reason. You know, either of those were fine. This was only pointed out to me by someone in the class. So if you proved that it was well defined, that's okay, but it's actually not for these 2 reasons. Same reasons, right? You know, f of 2 is going to be what, like 3/4 again. Okay. Let's do part C. Okay. Again, this is one that is also not well defined for a couple reasons. And you only have to give me one reason. Because once it's not well defined, it can't be like super it can't be super not well defined. You know, there's just, you're either well defined or not. So, okay. Anyways, let me try and give you a couple different reasons. First of all, f of 6, that's 0 since 3 divides 6. On the other hand, f of 6 equals 1 since 2 divides 6. 0 and 1 are not the same, so f is not well defined. On the other hand, f of 5, which is 2, since 3 does not divide 5 and 2 does not divide 5, but 2 is not in this set 0, 1. Okay, so f of 5 is not in the codomain, so it's not well defined. So you can either say for this reason or for this reason that f is not well defined. Okay, let's move on to question 3. This was about induction. Okay, so we're going to prove that every integer greater than 1 is divisible by some prime. Okay, so we can either do just straight induction, or we can use the well-ordering principle. I'll try and do both. Okay, so let's do solution A will be by induction. So let's say Q of n be the statement. P divides n for some p, for some prime p. Okay. Okay. Q of 2 holds since 2 is prime. Okay. Now assume the sum n greater than 2 that Q of k holds for all k lying between 2 and n minus 1. So what we're saying is that we're assuming that all the integers from 2 up to n minus 1 are divisible by some prime. Now we're going to try and show that n is divisible by a prime. Okay. So now either n is prime, and if n is prime, then n is divisible by n, so we're done. So the right end, we are done. Or n is composite. So d divides n for some d, which is strictly between 1 and n. Okay. But now this d is in this range. So we can say by induction hypothesis, P divides D for some prime P. Okay. Now, P divides D, D divides N, so P divides N. Okay. And in either one of these cases, we've shown that Q of N holds. So by induction, Q of N holds for all n equals 2, 3, on and on. Okay. Now in just this little space, we'll try and do it by the well-ordering principle. Okay. So let S be the set of n greater than or equal to 2 such that n is not divisible by any prime. Okay. If S is empty, then our statement is true, right? So assume S is not empty, then it has a least element by the well-ordering principle. So if S is empty, we're done. Otherwise, let n be the least element of S by the well-ordering principle. Well-ordering principle. And now we do the same thing. Well, if n is prime, then it's divisible by a prime. Okay. If n is prime, that's a contradiction. We have a contradiction. If n is not prime, it's divisible by some number in this range. That number is not in S since n is the least element. So that number is divisible by a prime. And that prime that divides that also divides n, and that's a contradiction. Okay, so I'll just, because I kind of ran out of room, I'll just put dots. But you just fill in what this part in here. Okay. So you can do the same thing using the well-ordering principle is all I wanted to say. Okay. Okay, so let's try, I'll say like some proofs, it's more natural to use a well-ordering principle, and some proofs it seems more natural to do something else. Okay, let's prove this. Solution. Let the statement P of n just be that GCD of fn plus 1 equals 1, where n, so n can go from n equals 0, 1, 2, and on and on. Okay. So we have to prove P of n by induction. Okay, base case is P of 0, which is just a statement that GCD of 1 and 1 equals 1, and that's clearly true. The greatest common divisor of 1 and 1, well, the only divisor of 1 is 1, well, plus or minus 1, really. Okay, so of course their GCD is 1. Now assume P of k, some k bigger than or equal to 0. That is, assume that the GCD of fk and fk plus 1 equals 1. Now we consider P of k plus 1, and we have to find the GCD. We have to find the GCD of fk plus 2, fk plus 1 with fk plus 2. But fk plus 2 is just fk plus 1 plus fk. Now the GCD of fk plus 1 plus fk with fk plus 1 well, we can take this and subtract this, and we get the same. That's the same as the GCD of fk with fk plus 1. So either you can use this as a fact, where we assume that the GCD of qa plus r with a is the same as the GCD of r and a. Okay. Right, so we can take the first thing and subtract any multiple of the second thing, and we have the same GCD. Okay. If you don't believe me, you should try to prove it yourself. For this question, it's okay. We'll just assume it. Okay, and by induction hypothesis, this is 1. So P of k plus 1 holds. So by induction, P of n holds for all n. And there is a little point I want to make here, and that is we can apply this formula since k is greater than or equal to 0. K plus 2 is at least 2, and that's when this formula applies for n greater than or equal to 1. In other words, n plus 1 greater than or equal to 2. And here, as long as this thing is at least 2, we can apply the formula. So here we use that k plus 2 is at least 2. Okay. And that's the end of that question. Now this is just a computation. You know, so we just use our calculator. This goes into this about, what, not quite 10 times, so 9 times. With a remainder, well, I will just have to use, because my phone is recording, I just have to use my, you know, scratch paper. Oh. Okay. And oops. Yeah. Okay. We get a remainder of 882. Unless I forgot how to subtract. Well, that happens too. Yeah, okay. And now 882 goes into 1019 once. Well, with a remainder of not that much. What, like, I guess 137. And 137 goes into 882. How many times? Almost 6 times, but I guess just 5 times. And then 137 times 5. This is pretty boring. Well, I guess it can go in 6 times. Yeah. And with a remainder of 60. Okay, now 60 goes into 137 twice with a remainder of 17. 17 goes into 60. How many times? I guess 3 times with a remainder of 9. 9 goes into 17 once with a remainder of 8. And 8 goes into 9 once with a remainder of 1. And now 1 goes into 8 times with a remainder of 0. Okay, so the GCD of these two numbers is 1. And now we have to write 1 in terms of 10,053 and 1,019. So let's try and do that. And the trick is to just use back substitution. Rewrite 1 in terms of 9 and 8. Write 8 in terms of 17 and 9. And always gathering up these remainders together. So here we have 2 times 9 minus 17. And what's 9? 9 is just 60 minus 3 times 17. Okay, so we get 2 times 60 minus 6 minus 1 minus 7 times 17. And to be safe, you should check that 2 times 60 minus 7 times 17 is 1. It is. That's 120 minus 119. Okay. And now we replace 17. Okay, so let me check off the ones I've used. This one. I've written 1 in terms of 9 and 8. I've written 8 in terms of 17 and 9. I've written 9 in terms of 60 and 17. Now I have to write 17 in terms of 137 and 60. Oops. Okay. And what's that? Well, 14 plus 2 is 16 times 60 minus 7 times 137. And now 60, that's 882 minus 6 times 137. And then minus 7 times 137. So now we get 16 times 882. Minus 96 minus 7 minus 103. So I have 16 and 103. Now I have to write 137 in terms of 882 and 1019. Okay. So now I gather up the 882s. So I get 119 times 882 minus 103 times 1019. And then I rewrite 882. Well, 882 is really 10,053 minus 9 times 1019. Okay, now I'm almost done. Once I didn't make any mistakes. Okay, now I need to figure out what is 9 times 119. Well, there's no shame in doing scratch work. Then we add 103. So we get that. Okay, and that's the end. So of course, all of these were equal to 1, so this is equal to 1. So we have our solution 119 and negative 1,174. And that is the end. Okay, well, I hope that wasn't there the whole time, but anyways, yeah, I just that's pretty much the end. If you have any questions, of course, let me know. Thanks for watching.